Now, the second lecture of Professor Justin McInroy about axial algebras. Please, you can start.
Thank you very much. Good morning, everybody. I wanted to begin by just recapping what we saw last time. So last time I spoke to you and I outlined quite a lot of motivation, but towards the end of my lecture, I gave you some actual definitions of things. So I just wanted to recap that to begin with. So I'm not sure I said last time, but I should have said that throughout my lectures, A is always going to be a commutative non-associative algebra over a field F. I'm not normally going to make any assumptions on the field F. It can be any characteristic, finite or infinite. Actually, a lot of the things I'm going to say hold over rings as well, but I'd rather stick to fields for this. I'm not going to assume that my algebra has any identity or unit. Yes, in general, it definitely won't do. Okay, so we saw last time about these things which I called fusion laws. And a fusion law was just a non-empty set F together with some symmetric map on which takes two elements of F and returns you some subset of F. And you can represent these in a table. And I gave you two examples last time. The first of which was the fusion law of Jordan type and Jordan type eta. And it just looks like this. And if you remember from last time, my convention for these tables is that I'm not writing the brackets. So 1, 0 here means the set which contains 1, 0, eta means the set which contains eta, and so on. And when I write just an empty gap, an empty space, that means the empty set. So the empty set is really different from the set which contains 0. So that's one of my examples, this fusion law of Jordan type eta. And my second example is this fusion law of monster type M alpha beta. And it looks like this. So alpha beta and eta here are, because F is a set, it means that, for instance, here eta can't be equal to 1 or 0. And here you've got to have alpha and beta different and alpha and beta not equal to 1 and 0 as well. So these four things I want to be for different elements of my field here, or will turn out to be anyway. Okay. And just more notation here. So remember that I'm thinking about the adjoint action of some element A, and I write A lambda A for the lambda eigenspace for A. And sometimes I'm going to drop this brackets A here where it's obvious. And similarly, if I've got some set here, so S is some subset of F. So I'm going to write AS of A for the direct sum of all of these A lambdas of A. And finally, spec A is just going to be the set of eigenvalues for this adjoint. And the way we define an axial algebra is as follows. So we define an axis. So given some fusion law, an f-axis, or I will often just say an axis, is an element of my algebra such that it is an idempotent. I'm also going to require it to be semi-simple. So that means it's diagonalizable, the adjoint. And in particular, I want A to equal A sub F. So what does this mean? It means that certainly all of the eigenvalues are contained in F, and that's just saying that spec A is contained in F. There may also be other things in F which aren't in spec A, but I'll say more about that in a minute. So I'm requiring that A is A sub F. And finally, I want my multiplication to satisfy my fusion law. So what I mean by that is that when I have a lambda eigenvector and when I have a mu eigenvector for some A, some axis A, then it's the product of those two things should lie in the sum of all of the eigenspaces which correspond to lambda star mu in the fusion law. Excuse me. So that is what an axis is, and an axial algebra or an F-axial algebra is going to be a pair AX, where A is a commutative non-associative algebra and X is a set of F-axes, and these F-axes must generate my algebra. Okay, so that was just a recap from last time. I'd like to make some remarks on this definition and say a little bit more about it before we move on. So one remark I definitely should have made last time and left you with is that axial algebras were introduced by Felix Rehren, or actually John Hall, Felix Rehren, and Sergei Shpectorov. Okay, so I should have said that up front. Following on from this definition, I just want to think about this part for a minute. A is an idempotent. That means that A lies in the one eigenspace for A. And that's simply because when you're an idempotent, A squared equals A, remember. So that's A times A. So A is in the one eigenspace for the adjoint action for A. And I want to say that an axis is primitive if the one eigenspace, axis A, let's say if the one eigenspace is just spanned by A. So this is my notation here for linear span. So that's as a subspace. So it's certainly true that A must be contained in the one eigenspace. And if that's the only thing in the one eigenspace up to scalars, I'm going to say my axis is primitive. And likewise, an axial algebra is primitive if all the axes in X, that's my generating set, are primitive. Okay, so this is a property which we're often going to assume. It turns out that certainly the Griess algebra is primitive. Lots of these Jordan algebras are primitive. So it's not an unnatural thing to assume. Okay, so what are my remarks on this definition? Well, firstly, and perhaps most importantly, note that all axes in my set X have the same fusion law? So this was explicit in my definition, but I just wanted to be very clear about this. We will lose control over the multiplication if we just allow every axis to have a different fusion law. We really want all of them to have the same fusion law. Okay, the second thing I wanted to say here is that just because we have two different axes, it doesn't mean that they necessarily look exactly the same. So what I mean by that is if I've got two axes, we can have that A lambda A and A lambda B, i.e. the lambda eigenspaces for A and B, have different dimensions. So nowhere in my definition did I require all of the dimensions of the eigenspaces to be the same. So if, in particular, if they're not the same, then there's going to be no automorphism, which takes one axis to another axis. In lots of cases, they will be the same, but they don't have to be. In particular, or maybe not quite in particular, but something which is sort of linked with this is that I'm not even requiring A lambda to be non-empty, to be non-zero. So it could just be the trivial subspace. And what does that mean? Well, let's go back to our fusion laws for a minute. We already noticed last time that the Jordan fusion law of Jordan type alpha, say, occurs in the top block here. So suppose I've got an axial algebra of Jordan type alpha. It is also a fusion law. It's also an axial algebra with a fusion law for the monster type alpha beta, where beta is anything, because all of my axes just have a trivial beta eigenspace. That's something which I allow. So maybe this is my third point here. This does not have to be non-zero. In particular, an axial algebra of Jordan type alpha, say, is also an axial algebra of monster type. Alpha beta, yes, my alphas match up, for all beta, and I'm going to have that beta doesn't equal 1, 0 and alpha. Okay. And I guess a more philosophical point here, in lots of examples of non-associative algebras, the algebra is defined with respect to some, as saying that it has to satisfy some identities of some sort. So for example, Jordan algebras are algebras where every element or every pair of elements satisfies this Jordan identity. you know, this x times y times by x times x equals x times y times x times x. So that's the Jordan identity. Lie algebras similarly satisfy the Jacobi identity, and also the brackets, a brackets a brings 0. So lots of non-associative algebras here satisfy identities. Axial algebras are defined in a different way. We're not saying that all elements satisfy a certain identity. What we're requiring is that certain elements, i.e. our axes, decompose our algebra in a nice way, and that the eigenvectors with respect to those axes obey the fusion law in the way I've set out in the definition of an axis. So it's really a slightly different mindset, a slightly different take on what you can do, or a slightly different way of describing, shall we say, a non-associative algebra. And precisely, so in the first case where you've got an algebra which satisfies some identity or some number of identities, that will give you control over the multiplication. You need some control over the multiplication, and in axial algebras, it's given by those two things: knowing that you have axes and that the eigenvectors with respect to those satisfy the fusion law. Okay, so 4 is many non-associative algebras are defined using one or more identities, e.g. Lie algebras, Jordan, we control our multiplication using the fusion law. Okay, so having given you the definition, I think we should see some examples. And my first example is the Griess algebra. So I think I said this in my motivation. Well, it is an example. It's not a terribly useful example for you and I, maybe, because I can't write it down easily. But it is an example, and it has the monster fusion law, 1/4, 1/32, that's meant to say, 32. Okay, so that example is somehow both the motivating example and too big, too complicated to do anything with. Certainly you can't do easy calculations with it. So what about another example? Well, let's go instead. Let's suppose that A be an algebra generated by, actually spanned by, A and B, where A squared is A, B squared is B, and finally AB is 0. So this is an axial algebra because I have two axes here, A and B. Those generate my algebra. In fact, they span my algebra. And what are their fusion laws? Well, let's just think about A. I have A in the one eigenspace for A, and B is in the 0 eigenspace for A. Similarly for B, B has also just 1 and 0 as its eigenvalues. And you can check. So let me just say here, so X equals A and B, and e.g. A1 of A is A, A0 of A is, those should have, these are subspaces. So A0 of A is spanned by B. And what about the fusion law? Well, I've certainly got 1 and 0, and I just need to know how those multiply. So A is an axis. If I multiply it by itself, I get back to A. So 1 times 1 is going to be 1. My one eigenspace times my one eigenspace gives me my one eigenspace. If I multiply my one eigenspace by my 0 eigenspace, well, that's empty. And what about my 0 eigenspace? So my 0 eigenspace for A is just spanned by B. And when I multiply B with itself, I get back B. So that is in the 0 eigenspace. So 0 times 0 is 0 here in the fusion law. So this is a very simple algebra. And it turns out to be an axial algebra. And in fact, by that comment I made just earlier, so that you see this is 1, empty, empty, 0. And remember I said that axial algebras for one type of fusion law can be another as well. So let's have a look back at our fusion laws. And I see this 1, 0, 1, empty, empty, 0 here. I also see it here. So not only is this algebra here an algebra for this fusion law, it's also an axial algebra for Jordan-type fusion laws for all eta, and it's an axial algebra for the monster-type fusion laws for all alpha beta. And actually, that is where this algebra gets its name from. So we call this algebra it's called 2B. That might seem a slightly odd name. The reason for it is that it is, as I said, it's an axial algebra for the monster type fusion law. And these were the first axial algebras considered. In fact, it's also a Majorana algebra. So these were the predecessors for axial algebras. And because of some naming conventions coming from the Griess algebra, this is a two-generated algebra. And the two-generated algebras of the Griess algebra are named after basically the, oh, this will become more clear later, but actually more clear at the end of today. As I said in the motivation, to every axis you can associate a an involution, and it just so happens that the product of the two involutions, in this case, is in the conjugacy class 2b, and so we end up naming the algebra like this. But you can forget about all of that and just call it 2b. Okay, so maybe I've given you one very complicated example and one very easy example. So what's maybe a more representative example? Well, I want to tell you about a family of examples called Matsuo algebras. So if you'll remember from my motivation, these featured there. So I'm going to start by letting G, D be a 3 transposition group. So just as a reminder, G is a group and D is a set of involutions. That's elements of order 2, such that if I conjugate D by G, by any element of G, this is just going to preserve D, so I don't get any new ones. And I'm going to require that G is generated by D. So there are a set of involutions which generate G. And more than that, I should only have one and the order of a pair of elements when you multiply them is 1, 2, or 3 for any of my involutions. So it's a special type of group with a special generating set. Okay, so suppose I have one of these 3 transposition groups. How am I going to define an algebra out of these? So let's just think about this a minute. Let AB be 2 of these. If let's say that the order of these is 3. Well, this happens actually if and only if AB is the group S3. So that's the dihedral group of order 6, another way of saying that. In particular, there's only one other. How many involutions are there in S3? Well, there's 1, 2, 1, 3, and 2, 3. So A and B must be 2 of these. So there must be a third. So there exists exactly one other involution, C, say. I mean in this group AB, which is of course in G. Okay, so one evolution not equal to A or B. So there's 3 involutions and I've named them A, B, and C. So, okay, so I'm now ready to give you the definition. So let M eta of G be the algebra spanned with basis D, and I need to tell you what the multiplication is. And so I take two elements and I multiply them. And what is this going to be? Well, if I multiply A with A, then I'm going to want to make this A. If I multiply A with some element where the order, so if the order of AB is 2, i.e. the two elements commute, I'm going to want to make this 0. And if the order is 3, so this would be order 1, order 2, order 3. Those are the only 3 cases. And finally, in this case, I'm going to want to make this eta over 2 times A plus B minus C. And this C is precisely this third C here. And actually, we know that because C lives in here, C here is equal to A conjugated by B. It's also equal to B conjugated by A. So if you want to know here, this C is A conjugated by B or B conjugated by A. So this is an algebra. And what value can I take my eta to be? Well, I take my eta to be not equal to 0 or 1. And this is an axial algebra of Jordan type eta. So that's why I've slightly scaled my scalar here, eta over 2. This thing is going to give me an axial algebra of Jordan type eta, and also it is primitive. So maybe we can see that. So things which are going to be in the one eigenspace for an axis. So this is obviously the 0 eigenspace. There's going to be some other eigenspaces involved here, but it's set. Maybe you need to actually write down what all the eigenspaces are. Okay, so exercise for the reader. Maybe not for all 3 transposition groups, but for the transposition group S3, where D is the 3 involutions, find the eigenspaces for the axes. Also, I guess, what are the axes here? Find the axes, and so show that this it is an axial algebra of Jordan type eta. So that's a very concrete example, which you can do easy calculations in. And again, for slightly esoteric reasons, this particular one for S equals 3 here, it is called 3C eta. And again, this has to do with the fact that at least the version which is just 3C came from the Griess algebra with the monster fusion law. Again, 3C refers to some conjugacy class. And so when we do this for general eta rather than a quarter, then we just call it this. Okay, so those are my examples. What I promised you this time, though, is that I would talk to you about automorphisms. So let's do that now. So perhaps the key property or the key feature of axial algebras is that they have a naturally associated group of automorphisms. So I guess the key words here are, I'm not taking all the automorphisms, I've got some subgroup, but the key word is naturally associated. So that's what I want to tell you how to get now. And the way we get this is via the fusion law. Okay, so I'm going to begin by telling you about morphisms and gradings of fusion laws. So just a note here that this definition here is the one which is the more recent definition, which comes from, so definition comes from a paper by Demetz, Peacock, Shpectorov, and Van Kouwenberger. And it turns out this is a nicer definition because it allows you to say more about the fusion laws, which I will touch on when I get there. But just to say it is equivalent to the previous definition. That is the original definition of Hall, Rehren, and Shpectorov. But this actually, I think, is phrased in a nicer way. So definition, let F1 and F2 be fusion laws a morphism of fusion laws, well, what should this be? It should be the obvious thing. It should preserve the multiplication. So it should be a map F from F1 to F2 such that, so it's got to preserve the fusion law multiplication. So if I do F of, let's say, lambda star mu in the first fusion law, this should be contained in F of lambda star in the second fusion law, F of mu for all lambda and mu in the first fusion law. And the reason why this definition of theirs is nicer with these morphisms is this, because this allows us to define the category of fusion laws. So this is my sort of aside here. I don't want to really get into it. If you want to see the details of that, you can read their paper. So this makes this allows us to define the category of fusion laws. And obviously here the objects are going to be fusion laws, and these morphisms are going to be the morphisms between the morphisms between fusion laws are going to be the morphisms in the category. So what's an example of a fusion law? So let T be an abelian group we define the group fusion law by, well, I need to tell you what the product is. So this product is just going to be the set which contains the single element S times T. Okay, so that is another fusion law. So I now have lots of examples of fusion laws, one for every abelian group. And why have I given you this? Well, this is the way we're going to define a grading on a fusion law. So definition, let T be an abelian group a T grading of a fusion law F is a morphism F from F to T, where I mean here the group fusion law T. Maybe I'll be explicit at this moment. To the group fusion law T. And a grading is called adequate if f of f, i.e. the full image, generates T. So, well, why do I want this definition of adequate? Well, suppose I've got a non-adequate fusion law. Then I never see part of my abelian group T. So I can always, in other words, if I've got any grading, I can always just make T smaller until I have an adequate grading. So this image is going to generate some abelian subgroup of whatever T is, and I just take that abelian subgroup and I have a grading by that abelian subgroup, which is adequate. So I can always consider only adequate gradings, which I'm going to do. Okay, and let me just note, so we will be most interested in C2 graded fusion laws. And here I'm going to use the notation. I use the notation that C2 is going to be just the group which contains plus and minus. And note, so examples of these, well, both the Jordan type eta and monster type M alpha beta are C2 graded. So why is that? It's going to be several pages back now, I think. Here we go. So I need to form a grading. So I need to know where I map my things. So for instance, here, I'm going to map these are going to map to plus. This is going to map to minus. So what I need is that this mapping preserves the fusion law. So notice that when I multiply any two things here, I stay within the plus part. And so in the plus part in C2 then, if I multiply plus with plus, I get plus. So I must be able, that's exactly what I have here. When I multiply any two things, 1, 0, and a quarter, I only see, 1, 0, and alpha, I only see 1, 0, and alpha. Likewise, if I multiply either of 1, 0, and alpha by beta, I get beta. And that's exactly saying that I'm multiplying a positive type thing with a negative type thing and getting negative. And similarly, I multiply beta by beta. Those both map to the negative graded parts. Negative times negative is positive. So I must only see things in the positive part, and I do. So the old definition would be to say that I have a partition here, and I just partition my things into plus and minus. But it turns out that's exactly equivalent. And right, so let me just get back to here. So both our fusion laws here are C2 graded. And I guess I want to say one other notational thing here. I want to, so suppose let F be T graded. If I have some, let me just write it. So I'm going to define AT to be the direct sum over all lambda in the pre-image. I'll make my F's look like before. Pre-image of my T of A lambda. So i.e. I'm taking the entire T graded piece, and that's what I'm going to call A sub T. Okay, and that notation is going to be useful for us because I'm going to use these gradings to define automorphisms. So let T star be the group of linear characters of T. So this is my abelian group T. So just recall this is the set of homomorphisms from T to my field F. Multiplicative group, sorry. Okay, so define a map tau of A of chi from A to A by, so what I want this to do is I want this to take some element U, which is going to lie in the T graded piece. And I want to take this to chi of T. So chi is my linear character here. So this is for A in X and chi in T star. K is a linear character. I can apply that to some element and get a scalar. And I'm going to use that scalar to times by U. So this is going to be, because A is semi-simple, this defines a map on all of A. So my axis A is semi-simple on A. So I get a map on all of A. So I'm going to define it like this and extend linearly. And lemma tau A of chi is an automorphism of A. Moreover, the map which sends chi to tau A of chi for some A, fixed A, is a homomorphism from T star, group of linear characters, to the automorphism group of A. So I guess I just want to sketch out some of this. So why is this an automorphism? Well, this is just acting as scalar multiplication. On the eigenspaces. And so in particular, if I multiply two things in two different eigenspaces, that should be multiplied by, what do I need to check here? So what I need to check is if X is in one graded piece and Y is in another graded piece, say, I need to know that when I apply these, so what is this going to be? This is going to be, so I'm applying this to the product here. This product, by definition, this lies in the S graded piece and in the T graded piece. So the product must lie in the graded piece, which is in S times T. So this is in the S times T graded piece. And that's just the definition of the map. Here I apply chi to S times T. But this this chi is linear, so homomorphism. So this equals chi times S times chi times T. But now we see chi times S times X and chi times T times Y. So this is exactly tau A chi of X, that's chi times S times X, times tau A chi times Y. Maybe I should put brackets in there as well. So what we've done here is we've shown that this tau is an automorphism. The second part I claim is just obvious. You can look at that for yourselves. Okay, so I think I'm just about out of time now. I should just say that we call this thing, which we now know is an automorphism, this is called a Miyamoto automorphism. And as a quick preview to next time, I get one of these automorphisms for each of my axes. And so I can look at the group which is generated by all of these different taus for all of the different axes and all different chi's. And this is going to generate a group. And this is this group of automorphisms which is naturally associated. Okay, but I'll go through that in detail next time. Thank you very much.
Let's thank the speaker for a nice presentation. Any questions and comments, please?
No? Okay, well, I will see you tomorrow morning at the same time then. Thank you.
Sorry, I have a question.
Oh, yes, sure, go on.
Yeah, I'm a theoretical physics student, so here's my question. What is the impact? What is an example of impact of this in physics? Because on your first lecture, you say that this was considered by physicists firstly.
Yes, that's a good question. I think it is underexplored at the moment. So actually, this is a relatively young subject, maybe in the last 10 to 15 years. And actually, there were a series of talks over the last maybe three months or 4 months or so, organized by Mario Maynardis and Clara Franchi in Venice. And that was actually bringing together people from the VOA's community with axial algebras and others. And I mean, vertex operator algebras have more applications or more known applications in physics. And actually, as I said in my first lecture, this was subject to sort of motivated by some of the things which you saw in VOAs. And actually, what we'd really like to do is have some of that go back the other way now and start trying to answer some questions in VOAs using some of this machinery. Because in a way, this has stripped out some of maybe some of the complications of VOAs. And we hope that we still get left enough structure, enough richness here that we can still say something about VOAs. So this is, I think, a very good future research areas.
Yeah, okay. Thank you.
Thank you.
Hello.
Hello.
First of all, thanks for the lecture. It was very interesting. My question is about the definition of morphisms you have done.
Yeah.
Morphism of Fison laws. You have written that the image of by the application F from Fison law F1 to F2, you have written that the image of lambda mu is include but not equality. Why this is not equality in the place of the inclusion, but you have written only inclusion. Can you in this definition, is this a reason?
Right. So yeah, it's true. I wrote contained in here. So I could be more strict and say equals here, but then this would rule out some morphisms, things which I guess if you know about categories, this would look more natural here. And so I have more morphisms here because I've put it like this. So I have morphisms from small things into much larger fusion laws here, where I'm not going to see all of the fusion law. Yeah, I'm not going to see all of this second fusion law by just mapping my small one inside it. Think of this like group homomorphisms or algebra homomorphisms. I'm not going to see all of my the second algebra or the second group here. but I still want to be able to, for instance, have a morphism from the trivial group or the trivial algebra into all other algebras. Similarly here, I want a morphism from the trivial fusion law into all of the fusion laws. Yeah. If I have equality here, I'm not necessarily going to be able to do that. Actually, a concrete example of this would be, I could create a, where's my, one back, one more. So a concrete example would be to have a morphism from the Jordan type alpha fusion law. The obvious morphism is to map it into this part here, the positive part, but a non-trivial, like a more non-trivial morphism would be to map 1 to 1, 0 to 0. This eta I could map to the beta here. And then eta times eta is 1 and 0, but beta times beta here is 1, 0, and alpha. So I would never see this alpha. I want to allow that morphism.
Any more questions and comments? So let's again thank Justin for nice lecture.